Thank you. I like the emphasis on the word long. I think time has been long. I was really honored to be invited to speak today about sensing. I was also, quite honestly, a little bit trepidated. Talking about sensing in general is obviously a huge topic. The other thing is that when you start to talk about sensing and robotics, it can be a little bit dangerous. This is literally a quote from a couple of years ago from someone. Why would I add a camera to my robot? It costs me money, it makes it slower, and it makes more mistakes. What's the point of that? So, sensing is a hard problem. We've been working on it for many, many years. I think, however, that in the last few years, we've seen really a number of revolutions in the world of sensing. And what I'd like to do in this talk is give you a sense of really what the progress has been. I'd like to point to a couple of key things that have happened in the past and how that has accelerated progress. And then I'd like to look forward a little bit where I think sensing is going to go, particularly, as I hint in my title, as we start to live in a world where more and more sensing is simply part of the environment. I should point out, maybe to start with, that sensing is not only a hard problem for us, it's a hard problem for biology. More than half the brain is devoted to some type of processing, whether it's auditory processing, visual processing, sensation, taste. So you spend a great deal of your brain cycle simply processing information from the world around you to get through your daily life. So to expect that we're going to solve all of those problems in robotics immediately, of course, would be unreasonable. And so the question is, where are the places that we can make progress, and how can they have an impact? So to put this in a little bit of an historical perspective, this goes back really to when I was a PhD student. So this is a GRASP lab in the mid-'80s. And this is showing literally a setup that, in fact, Peter Allen, my colleague, used in his PhD, and I also and some other students used. And what's interesting are two things about this. The first is that if you look at what's in this picture, much of what you would expect in a modern robotic system is already there. So you see a pair of stereo cameras. There's a tactile sensor down here. There's a force sensor. And then I'm showing some other force capabilities from a similar time period. So we really had a lot of the basics of sensing as much as 30 years ago. Maybe the difference is, though, that they were really a scarce resource, and they didn't really have the performance that maybe we would like of them to have had. So that cup that's sitting there is not lightly touched by that tactile sensor. It's bolted to the table so that it doesn't slide around while we do the experiments. Well, the good news for us is that sensors are scarce no longer. So this is the PR2, and there's more than a dozen sensors of many different modalities. So the ones that I already mentioned, so there's certainly force, there's tactile, there's video, range sensors, RGBD sensors, so a wealth of sensors that can now be used. So we don't live in a world of scarce sensing resources anymore. We don't live in a world where there's a paucity of data. But perhaps more importantly, it's not just on robots. So when we used to do research on computer vision, I used to think, we're really one of the few places in the world or in the country that has, high-quality color video cameras that we can get digital images with and we can process them. Well, now all of you are probably carrying 1, 2, 3, 4 or more of those cameras around with you everywhere you go. And you upload it to the web constantly and Facebook it and label it and all that good stuff. On the right is a plot showing the growth of network surveillance cameras. There's now more than 250 million network surveillance cameras in the world, and it's growing rapidly. If you add those to the iPhones and the laptops, we're getting close to 1 billion cameras in the world, so 1 for every 6 or 7 people on the face of the earth. And of course, you all know about the Kinect. It was originally invented for gaming. It's consumer grade, but it's cheap, highly available RGBD sensing that, again, has really transformed many areas. So we really have the hardware, we've got the data, so what's the problem? Well, so it is the fact that going from data to information is hard. So you do need the algorithms to actually make that transformation. And I thought a great illustration of this is in the area of SLAM. So this is a Pioneer robot from maybe 20-ish years ago. You can see it's got the ubiquitous Polaroid sensors on the front. Everybody remembers sonar and how much fun that was. Well, at the time, trying to build a navigation system was tough. One of the key pivotal works at the time was work by Smith, Self, and Cheeseman on Kalman filters to build SLAM systems from sonar. Now the fact is it was great work, and they actually got very nice results. You could now make a robot perhaps move down a corridor and keep track of its position. But the fact is it wasn't really practical at that point. And in fact, the best example of this is a company called Helpmate Robotics, which in fact tried to build such a system based on sonar-based navigation and went out of business because they couldn't make it work. So the change came when we started to mount laser scanners on robots. So a new device came into being, and with that new device, not only did it give us a new source of data, which we just talked about, but also it let us start to invent new algorithms. And it was really this coupling of a device that gave us a new type of data, and it allowed us to think in a different conceptual space about designing algorithms. For example, you could do scan matching, which you couldn't have done before with a sonar sensor. And so with this, we have obviously went from Kalman filtering to particle filtering, and eventually to algorithms like FastSlam, which really now have enabled amazing progress. So we've gone from that corridor to building, to going through buildings, to going through campuses, and this is work by the CIRO group in Australia, where they're actually taking a LiDAR system and they're driving around country roads, and they're mapping out miles and miles and miles of country roads. So it was really a combination of having the right sensing and having the right algorithms and putting the two together and then being able to build on that. That's allowed this amazing progress over the last 3 decades. One other story I wanted to tell just to illustrate a point is object recognition. So object recognition is arguably one of the oldest, most key problems in computer vision. It's the problem that's probably most associated with the field. So we've worked on object recognition for since the 60s. And if you go way back, so Rod Brooks, who many of you may know, actually did his PhD thesis in computer vision. It was AI reasoning to recognize objects and images. And it was really one object. It was an airplane. If we go ahead 10 years, there was a lot of work on constraint-based vision, and people were getting up so they could maybe do a handful of objects. So we saw, maybe arguably an order of magnitude progress in 10 years. In the 90s, the big excitement came to be appearance-based recognition. So this is the work of Sri Nair and his group. So on the one hand, this is great progress because we're now able to recognize tens of objects. But you notice it's a step backwards in that this is a very artificial background. So we're recognizing objects, but we're really not recognizing them in situ, in realistic conditions. So if you think of it, when I gave a lecture in computer vision in the late 90s, and I would talk about object recognition, mostly what I would talk about with students was to say, well, there are a lot of great ideas out there. None of them have really transpired to work in any scalable way in object recognition. It's a completely open problem, and furthermore, we don't even really know what the solution path is. So that changed just about 15 years ago. So in the late 1990s, early 2000s, David Lowe invented the SIF feature, Scale Invariant Feature Transform, and that was literally transformational to the field of computer vision. In the space of 2 or 3 years, you went from a problem like object recognition, where people really did not know how to make progress, to suddenly having effective, scalable solutions that really worked in realistic environments. They could work under occlusion, they could work in change in orientation, they could work in change in lighting conditions. So complete transformation of the field in a very, very short period of time, to the point where now object recognition was considered, if not a solved problem, at least a problem very much like that SLAM problem, where it's incremental advances to make it better and better and better, but the solution path was somewhat clear. And I would argue that if you ever wanted to point to a breakthrough in a field, this is probably the closest you'll come to something that was just an iconic breakthrough. At least one measure of that was, I went to Google Scholar to look up the site, and the 2 papers on SIF features have accumulated 38,000 citations in the last 10 years. So just about anyone in the field of computer vision has used it, has cited it, and it is now something that the field builds on. So the last thing I'd like to talk about before moving ahead is, so this illustrates a breakthrough. The other piece of moving a field forward is, how do you keep track of progress? So for example, in object recognition, one of the big opportunities and challenges is availability of data. So you can now download terabytes and terabytes of vision data, and you can develop your algorithms using the weak labeling that's out there on the web. But how do you know if you're making progress? And in fact, what the vision community has been very good at has been creating new benchmarks, open data sets, public metrics for performance, and then the community actually using those metrics. So no longer can you just publish a paper on your narrow topic with your algorithm and your data and publish it. You really have to compare it with what the community is doing. And I think from the point of view of sensing, creating these sorts of data resources is really a key step toward moving the field forward. So I've talked about mapping, and I've talked about vision. I could talk about many other areas. Here's an example from speech. Speech has just made remarkable progress over the last 2 or 3 decades, to the point that now, of course, you can talk to your phone. And just to give an example of work that we've done, tactile sensing. I showed you that tactile sensor that you had to bolt the cup down. Well, you can now get reasonably high-quality tactile sensors, and in fact, by stealing some of the algorithms from computer vision, we're able to show that we could do keyframe-based or SIFT-based recognition of objects from tactile images, very much the same way that you would do it in computer vision. So I think if you look at the broad set of topics that we're covering, really we've made lots of scientific progress, in part through technology, in part through algorithmic innovations, in part through community engagement. So where does this go? Well, so one thing I'd like to argue is that economics ultimately drives much of this technological advance. In fact, if you look at Moore's law, it's an economic law. It's not a technology law. It says the cost per transistor is the lowest, or the point where the cost per transistor is lowest is what doubles every 18 months. And in fact, the reason the iPhone 5 has all those sensors is because it creates new and interesting apps, and that's what actually funds a lot of the commercial side of the business. And the Kinect was, of course, made for gaming. So what are the next new drivers? Well, so there's been a lot of hype and discussion recently about the Internet of Things, or the Internet of Everything, depending on how you talk about it. So while there's been a lot of discussion, and it may sound like hype, on the other hand, I do think it's actually true that, as I've already said, the world around us is becoming more and more sensorized. There's actually very little that we do at this point that some sensor would not actually be able to pick up in one form or another. So we really can envision a future where sensing is not just a sensor on a robot. Sensing is everywhere in the environment around us. And so the question is, how do we now move the field forward in a world where we're awash in a sea of data? So one of the things I wanted to illustrate in this Internet of Everything is some work by the UbiComp lab. It's Shwetak Patel at the University of Washington. Just giving you an example of the sorts of things you can start to imagine doing when you couple machine learning and data and devices. This is figuring out what is on in your home and what's using electricity. So every time you turn on a device, it generates EM interference on the line. And so what they were able to do is to build a sensor for EM interference. Then we apply some machine learning. They're actually able to build a classifier that can say what the source of that EM interference is. And now they can actually log what's using energy in your household at any point in time. But not only that, they can actually log what your activities are at any point in time. For example, they can now start to say, well, this household always does wash on Saturdays because that's when the washing machine comes on and off. These people tend to stay up late. These people tend to get up early. These people never cook because the lights in the kitchen never come on. So it's a cool technology, but you start to think of, well, what are the other things that you could do with it beyond just compute your electrical bill? And I think that's where we need to start to be thinking about is what are the sources of information we have in the environment around us and how can we use them? So here are some challenges that I'd like to end with in terms of how we think as a field of moving forward in the world of sensing. So the first thing is making sensing disappear. So by that, what I mean is right now, I think there's this notion you buy a sensor and you put it down and you do something with it. Really, you should buy a sensor and it plugs into your environment. So the thermostat on the wall, the RGBD sensor that's running the Kinect, something that's sniffing your electricity to tell what's on, that's all should be part of an open plug-and-play sensing environment. And I want to emphasize open. We should really make this an environment that any sensor can plug in and you have access. Furthermore, those sensors should organize themselves around information, not data. They should be able to say, I provide, for example, information about occupancy, or I provide information about energy use or activity, not I provide an image or I provide a force reading. The second challenge, and I think, again, this applies broadly to sensing, is how do we create information APIs that we can actually use to answer questions? So again, if I think of a developer who's going to try to use sensors, they're not going to understand how sensors work. They're going to want to ask a question and get an answer. Who's in the house right now? Is somebody watching TV? So somebody could be watching TV because they know the TV is on and they sense motion in the living room or pressure in the living room, and the lights are on in the living room. Is my 2-year-old tell me when my 2-year-old is getting near the stairs so that I can go and deal with a potentially harmful situation? Who has the car right now? Which having a teenager in the house is becoming more and more a question I'd like to answer. Last challenge, implications for society. So this is something I'd like to have you maybe stretch your minds a little bit on, that, again, think not tomorrow or 3 years or 5 years, but 10 years in the future. We're already sharing lots of information. When you download a new app for your iPhone, you almost inevitably say, do you agree to share this information or that information? And right now we do it in fairly narrow channels because we believe that this app is going to give us some value for the information that we share. But imagine a world where, again, sensing becomes ubiquitous and you've got, let's say, 1,000 different devices in your home. It's easy to imagine this, 1,000 devices in your home, all of which might be gathering information or regulating some part of your environment. Are you really going to go to all of those and say, yes or no, I do want to share the information about my lighting system, but I don't want to share the information about my TV use, for example? So how do we know what information we're sharing and with whom? Perhaps more important, what can be inferred and by whom and for what? So as you share information, it's very difficult to know how these things mash up. So a great example of this was Target was actually able to target ads to women who they believed might be pregnant, not based on any information other than looking at surrounding purchases and things like that. So these women had no idea that Target was doing this, but suddenly you're getting ads that you may not even find appropriate. And we could imagine that happening much more broadly within our community. And last and not least, we talk a lot about safety and robotics. And I think we think about safety as something where the robot's going to hit us and we want to make sure the robot's safe so it can't hurt us when it hits us. But what about information leakage and how that might actually affect the behavior of physical devices in our world? So if I'm actually sharing a lot of information about my aged mother so that she can get assistance in some form, well, what might be happening in her physical environment that might actually harm her based on information that I'm sharing? And I just have the example of the Home Depot data breach. The Target and Home Depot data breaches were an information security breach, but they were a device breach. They were actually hacking the devices themselves to get information. So let me just close by talking a little, just saying, I think there are really 3 themes that I'd like to emphasize for the field going forward. The first is thinking expansively. I think in the world of sensing and the world of robotics, it's very easy for us to get focused on our own little problem and not think about how what we're doing may apply more broadly, and in particular in high-value applications in healthcare, the home, or the workplace. Also think generally. So when you look at the real breakthroughs in our field, those were fundamental concepts that were developed that changed the way people thought about problems. So again, it's great to optimize, it's great to do a little bit better, but try to think fundamentally about the problem you're solving and how you can develop new methods that might actually change the way people think about that field. And last, and perhaps most importantly, think openly. So again, to borrow a page from the computer vision world, I think it's key that we all share information with each other, we share data with each other, and we actually build on each other's work through that sort of open sharing. And I think the more that we as a community can encourage that and make that part of our way of doing work, the better off we are. So with that, let me close. I've got 27 seconds left. Thank you.
Hi, I am Alexandre Boeuf. I'll be presenting an approach for introducing context information in base filtering on the behalf of the authors of this work, who unfortunately couldn't be here today. Base filters are widely used for state estimation in robotics. They rely on the simple hidden Markov model representation, which contains 2 main components: a prediction distribution to predict the state value, knowing the previous state, and an observation distribution associating a measurement value to each state. This model is fast and simple, but often too simple to model the system realistically. Especially that measure reliability might change over time according to the environment. To compensate for this simplicity, unknown aspects of the real system are usually represented through the introduction of noise parameters, but the classical model uses a single and static observation distribution for all these contexts. In this work, the goal is to keep simplicity and time efficiency of the HMM framework, but make it explicitly able to model the context influence over the observation distribution. This task is achieved by first introducing a new context variable, then based on this variable, models are trained for both measurement noise prediction and measurement selection. Time efficiency is maintained by using a sparse Bayesian model, which is the relevance vector machine. At first, contextual information are gathered from different sensors. This contextual information is used as the input of a RVM regression model for predicting observation noise in the current context. In the same way, it is also used as the input of a RVM classifier to select the set of useful measurements. The rest of the inference for state estimation is then similar to any basic Bayes filter. By training such models, the system is automatically able to adapt to the whole range of sensor performance alterations, and hence does not require the tuning process usually required by the Bayes filters. I love to try and give you more details during the interactive session, and will provide results of the proposed approach in the context of altitude estimation for a quad rotor. Thank you for your time.
Hello, my name is Alessandro Piropang and I work in KTH Stockholm. And I'm here to present our work in the context of action recognition for robot learning by demonstration. Usually, this kind of problem is addressed by gathering data from a single modality and try to perform action recognition with the data you have. However, each single source of information has limitation. If you think about, for instance, at computer vision, vision may suffer from object occlusion while performing an activity, or the activity can be performed out of the field of view of the robot. And therefore, the information you get is incomplete. If you think then about the humans, we as humans formulate a coherent interpretation of the world by merging multiple modalities. And so if we want to have a robot that can operate in an unconstrained environment with humans, such capability is very useful for the robot. Therefore, what I'm presenting here are some experiments using multiple sensory, because the big question is, if we have multiple sensor and multiple modalities, how we can use this to classify activities, and how can we merge them to have a better classification? So in our work, first we use audio and visual features extracted from the raw data, and then we design a model taken from speech recognition to first classify using the single source actions, and then compare the results with the fusion of the two. And we found out that by fusing them, we can have a better classification rate for action. To do all these experiments, we recorded a data set that now is available online, and the data set includes 145 videos, audio tracks recorded with the Kinect, and there are 8 actors performing activity without any specification on how they have to perform the activity, or knowledge on how we extract features from the videos. And then we use an in-house tracker to extract object models from the videos so that we can have the complete synthetic scene and study the synthetic scene. And plus, we provide also the 3D models of the object we use in the activities and Python script to work with the data. So if you want to hear more about my experiments or the data set, just come to my stand. Thank you.
Hello, my name is Christian Müller, and I will talk about object shape categorization in RGBD images using hierarchical graph constellation models based on unsupervised learned shape paths described by a set of shape specificity levels. This work has been developed in a Warplock project. It's a EU project that tries to develop an autonomous cognitive robot for unloading of shipping containers. And we can see here in the video how this robot goes in a container and tries to grasp an object for unloading. There are several tasks involved. One of them is detection and classification of objects. And this is the one which we focus on this work. The problem is quite challenging, as you can see, the vision problem. So there are lots of different objects of various dimensions, types, shapes, occlusions, deformations are even present. So none of this object is really fully visible. Moreover, we are focusing here on a categorization approach rather than on an identification approach. So we would like to classify objects independently of their physical dimension, texture, pose, deformation. So we would like to generalize the appearance of boxes, barrels, and so on. For that, we use a part constellation approach. So there are several steps involved, like the oversegmentation, the part extraction, description, and so on. Due to the time constraint in this presentation, we only focus on the modeling, constellation modeling. So let's say we have already extracted some parts from the environment from an object. We represent these parts in a graphical manner using some symbols which we have trained beforehand. This is actually our dictionary. And then we try to train a set of constellation models of different classes. We use an energy minimization approach, which consists of a Markov random field-like technique combined with some statistical features to find the most appropriate class for this unknown part graph. So as you can see, this is actually a flat representation. We have just one symbol set and one set of constellation models. Now, our major contribution here is a hierarchical approach. So we subdivide feature space in several levels. Each of the levels will provide a set of symbols which we use for constellation modeling. And if we now pass through this unknown part graphs to each of the levels will return a classification result. So it's an additional evidence which we use for more complex classification result, which is actually better than only using a flat representation like here shown. Moreover, the observation is here that on a very high level, here we can only distinguish between simple shaped parts like curved and flat ones, and the more we go down, the more we can distinguish more complex shaped parts. And this words or this symbols we use for each of the constellation models, and this is actually our key of the approach. So here's a little demonstration. So we have here point cloud. Here's some intermediate steps which I didn't discuss here. And at the end, we get here final point clouds which represent the objects. So if you would like to know more about the intermediate steps like the oversegmentation, the part extraction, description, the instance detection, and so on, we can talk in an interactive session. Thank you. We have 5 more seconds. So you see the pre-processing takes most time, and the classification is pretty fast.
Hello everyone, my name is Myung-Soo Park and I'm from Korean Institute of Science and Technology. Today I will talk about my recent research result on SEMG-based decoding of human intentions robust to the change of electrode positions. SEMG means the electrical potential measured by a set of electrodes attached to the human skin. This is generated from muscles following human intention. Therefore, from this signal, we can decode the human intention behind the motion. Therefore, this decoder can be used to construct a user interface for main systems. However, there is one practical issue to be resolved. Electrode for measuring SEMG is generally tightly attached to the human skin, but it is very inconvenient. And from time to time, we have to detach and reattach these electrodes, but from these steps, the electrode position is likely to be changed, and it has the effect to change the definition of the input value of the decoder, so the performance of the old decoder cannot be maintained after the electrode position changes. For resolving this difficulty, I devised a new decoder using independent component and its matching algorithm. Since the source of the SEMG signal, that is the muscle, is not changed, therefore, if we apply the ICA to the SEMG signal, then we can get almost the same set of independent components before and after the electrode position changes. Therefore, however, the magnitude and order of these independent components is not the same, so we need a method to match the old and new independent components. By using this Once the matching is completed, we can use all the decodes as it is with a good performance by using the new independent component as the input corresponding to the old independent components. Finally, detail of the method will be explained in the interactive session, and from here I will introduce the experimental evaluation result simply. As these results show that the old decoder's performance is degraded after the electrode position changes about 90 level of the people performance. Past performance, but the performance of the new decoder is maintained at almost the same level before and after the electrode position changes. Thank you. This is my end of my presentation. Thank you.
Hi, I'm Pratap Tokekar. I just finished my PhD from the University of Minnesota. This is work with my PhD advisor, Professor Volkan Nishlor, and with Dr. Antonio Franchi from LASC and RS in France. In this paper, we study the problem of tracking a set of targets that are moving on the ground using a team of aerial robots. Each robot carries a camera that is facing downwards. What we would like to do is plan for the motion of the robots in order to track all the targets. Now, if our objective is to simply track all the target, here's a simple solution. Just have all your robots fly as high as possible. As the robots go up, their camera footprint increases. Eventually, it will be big enough to encompass all your targets, and your problem is solved. However, this comes at the expense of your tracking quality. As the camera footprint increases, the area that is covered by a single pixel will also increase, thus decreasing your measurement quality or your tracking quality. So in terms of your tracking quality, you would want to be as close to the targets as possible. But now you run the danger of not being able to track all the targets. So there's a trade-off between your tracking quality and the number of targets that you track. Our first contribution in this paper is a negative result. We show that it is not possible for K robots to track more than K targets while maintaining the optimal quality of tracking at all times. And this result holds even if you allow the robots to be faster than the targets, or if the targets move only on a single line, or if you say that you want to maintain only an approximation of the optimal quality and not necessarily the exact optimal quality. So in light of this negative result, we focus on the two objectives separately. So we formulate two versions of the tracking problem. In the first, we are simply interested in maximizing the number of targets that we track, subject to some minimum quality of tracking per target. In the second version, we are interested in maximizing the total quality of tracking over all the targets, over the targets that we track, and we don't worry so much about the number of targets we track. Right? Our contribution here is a positive result. We present a constant factor approximation, a 2 approximation for this problem. And we evaluate our formulation through simulations and experiments. I would be happy to talk more about our formulation, about the algorithm, the analysis, the simulation, and the experiments if you stop by our poster. I would like to let the video play out, and thank you for your attention.
Hi, everybody. My name is Chuan Zhang. I'm a master's student under the supervision of Yanis Ruklaitis and Gregory Dudek from McGill University. So in this work, we wanted to develop a fully autonomous indoor navigation system that would navigate around the environment, explore it, and map it out. Metric and topological maps are two of the most common ways that people are currently mapping the environment. But we believe that there's a natural synergy between these two methods. And we hope that by building a hybrid metric topological map instead, we can leverage some of the advantages from both strategies. For the topological representation, we're using a generalized Voronoi graph because the midpoints of the GVG are essentially correspond to the intersections of the environment. And we can also compute the GVG very easily in an online fashion using 2D laser scan data. To explore the environment, we essentially follow the GVG until we reach a midpoint. Whenever we reach a midpoint, we want to figure out which way we want to go to next. So we picked the first counterclockwise unexplored direction that we haven't visited yet. And by doing this, we're essentially closing the ears of the environment. Ear-based exploration is useful because, first of all, it enforces that we have systematic loop closure, but it also guarantees that we're going to explore the whole environment. We can bring in some metric information at this point by keeping track of the state of the meet points and the robot using an extended Kalman filter. And whenever we visit previously explored meet points, we use this information to update our Kalman filter and reduce the map's uncertainty. So here are some results of a robot running around the building. What you'll see is the red path denotes the raw odometry. The blue circles are 3 sigma uncertainty ellipses. And what you notice is that the raw odometry is pretty poor at this point. And it would be very hard to localize yourself based on this information. But thanks to our loop closure strategy, we're capable of keeping the topological information of all the meet points at the correct locations. So what you see right now is the same meet points overlaid on top of the ground truth, which is built using G-mapping. So we have some other results that we'd like to present to you. Currently, we're looking into comparing different relocalization strategies so that we can further reduce the map's uncertainty. The code is completely developed for ROS platforms, and it's available online on GitHub. So I look forward to seeing you all at the interactive session. Thank you very much.
Good afternoon, ladies and gentlemen. I am Roberto Arroyo from the University of Alcalá de Henares in Spain, and I am here to present our work entitled Fast and Effective Visual Place Recognition Using Binary Codes and Disparate Information. The main goal of our approach is to achieve a robust topological localization in lifelong scenarios. For this, we need to detect loop closures for identifying previously visited places. Our goal is to improve the current state of the art using binary descriptors and disparate information. We have achieved an average precision superior in 25% to FabMap, 23% to BrickGIS, and 16% to BrickGIS. Our method is called ABLE-S, which is the abbreviature of Able for Binary Pairs Loop Closure Evaluation Stereo. We implement as core of our method a global binary descriptor called DLDB, which is an extension of the original local difference binary, adding disparity and intensity to gradient information. We use disparity with the aim of reducing perceptual aliasing, and we have tested our approach in the challenging KT odometry dataset, where we provide a new ground truth for loop closure evaluation. Now we will show an example of loop closure evaluation in the sequences of the KT odometry dataset, where you can see how our proposal works in outdoors, and you will see how the loop closures are successfully detected. This is the video where you can see the reconstruction of the map using visual odometry, and you can also see the disparate information extracted for stereo images, which is used in our binary description of scenes jointly with intensity and gradient information. After completing the first lap, the initial zone previously traversed is revisited, and our method detects the loop closure, which is marked in green and can be used for correcting the accumulated error in visual odometry. As you can see, here it is marked the loop closure. Here we have some results for our method compared to the state of the art for the sequences of the KT odometry previously presented. As you can see, in the showed distant matrices, loop closures appear as red diagonals in the distant matrix. So in the distant matrix provided by our method using the DLDB descriptor, it can be shown how the noisy squares which appear around the loop closure lines are clearly reduced with respect to other approaches. All the previous affirmations are supported by the presented precision recall curves, which can be now seen for the sequences 0, 5, and 13 of the KT odometry dataset, jointly with the table presenting the main average results and times, where it can be seen how our method is faster and more effective than WeSurf or BrickGIS. I hope that you enjoy our presentation, and thank you. And if you want to do any question, we will be in the interactive session. Thank you very much.
Good afternoon. My name is Alexandre Eudes from ISIR, and I will present you my work in collaboration with Pascal Morin about a linear approach for homography, filtering, and estimation from visio-inertial sensor. The typical situation we have here is a visio-inertial sensor looking at a planar scene. This sensor is composed by two devices. First, a camera. This camera is used thanks to computer vision techniques to estimate homography. This homography measurement is related to the pose of the camera and to the normal of the scene. As we are in a molecular scheme, this measurement is defined only up to a scale factor. The other sensor we have is an IMU that provides us the angular velocity and the specific acceleration, that is the sum of the gravity and the linear acceleration in the EMU frame. What we try to estimate from those measurements is the rotation and the translation of the sensor. And for that, we need to estimate the UNO scale factor coming from the vision. We also want to estimate the velocity of the sensor, and as a byproduct of the algorithm, we will be able to recover the normal and the gravity. What it is done in the classical way is to, for those sort of thing, is to rely in a nonlinear estimation technique by put all the estimate in the state and using nonlinear estimator like EKF. But usually this sort of technique didn't provide a convergence proof. What we propose here is to lift the state in a higher dimensional space so that the state becomes a linear system. And with that, we prove that this system is observable if we have enough linear acceleration. And in this case, we are able to use linear Kalman filter. We also provide a Lumberger-like observer. Thank you for your attention. I will answer your question during the interactive session.
Good afternoon. My name is Michael Blush, and I'd like to present work I've been doing with Samuel Murray and other collaborators at ETH Zurich. The work is about fusion of optical flow and inertial measurements for robust ego motion estimation. The main motivation of the work is that when you're working with dynamic robots that you have to stabilize all the time, it might be interesting to do feedback control on the velocities and inclination angles of your state. But for this, you have to estimate those states. And we argue that in some cases it's more interesting to have a robust state estimation rather than an accurate state estimation. We also like to be able to handle fast motions. So the approach we propose is to fuse optical flow and inertial measurement. So on one hand, we're using a monocular camera where we implemented a KLT feature tracker, and we propose a novel optical flow-based constraint in order to extract the information out of those feature tracks. The advantage here is that we don't require a 3D feature initialization and that we avoid long-time feature tracking, both increasing the robustness of our framework. On the other hand, we have an IMU, which gives us accelerometer and gyroscope measurements. And this provides us with information on the scale and on the inclination angles of the robot. Those are generally affected by bias, and the filter will have to take care of this. We plug both these measurements into a non-centric Kalman filter. The overall structure of the filter can be seen on the right side. I will not go into details here, but I'd just like to mention a few points. So we use a robocentric formulation of the states in order to avoid problems with unobservable states. We co-estimate the inverse scene depth in order to be able to to formulate our update step. Then we perform a tight fusion with the IMU measurements, whereas we co-estimate the IMU biases. And we implemented an outlier rejection method and could also show that, in general, only absolute position and the yaw are unobservable. So here on the right side, you see the video stream of one of the data sets that we recorded in order to evaluate our method. And on the right side, you have the corresponding results. And we'd like to mention that we have rotation rates of up to 180 degrees per second, and that it was able to manage it rather easily. Yeah, if you want to see the plots in more detail, please visit the interactive session. Thank you.
Hello, my name is Iki Arianto from Taiyohashi University of Japan. Today I will present my works on cameraman robot. Usually when a director makes a film or commercials, it's usually limited by the time frames. It is about about the money. And then we often see about the structure, real structure called dolly track. It makes to the stable camera movements, but the problem is we need to change the track for every different movement type. So we propose a trackless-based cameraman robot. We want to make and change the desirable trajectory by just draw it, and we will support the time constraints. And if the actor is moved, then we will maintain the same viewpoints when the static actor happens. Our approach is basically to bring the robot trajectory from the 2D space into the 3D time space, and then we make an optimization problems, while the constraints, we make it into the cost map. After we make the cost map, we then bring it into the using the wavefront potentials and then do the randomized tree control to make the control for the robot. So basically we have make several kind of experiments using a 3D simulator. The scenario is to make the actor to be in the middle of the camera viewpoints. So for example, here the trajectory of the robots, we need to make it a half circles, while the robot maintains the movements into the moving target. We want to make the same viewpoints. So even the scenario is changed into the straight trajectory, we will also still maintain the stable movements and stable camera view in the camera of the director. Then, even if we add some obstacles like in the figures, we will still maintain the same camera view in the middle of the director camera, and then we will show another kind of scenario in the interactive session. So see you in the interaction section. Thank you.
I'm Teresa Vidal-Calleja from the Center of Autonomous Systems in Sydney. I'm going to talk about automatic detection and verification for pipeline construction features with multimodal data. So pipes break, and we need to inspect them before they break. So some sensors commonly used are external or internal. The commercial tools are usually driven by the flow, and they are provided with acoustics or magnetic sensors to be able to estimate the condition of the pipes. However, these sensors have a small field of view, and some robotic sensors do not work immersed in fluid. So how do we localize these the tools inside the pipe? So what we propose is to map construction features such as joints with an extra help. So we want to detect, identify, and verify the construction features with using multimodal sensors such as a camera. and a remote field eddy current sensor, that is the inspection sensor. This remote field eddy current sensor provides the phase and the amplitude of the magnetic field. We need to extract features and in this case we propose to extract peaks and valleys and describe them with a with a descriptor based on Hort parameters. We classify these features between either being construction features and not construction features, and we can go even further to classify joints and other construction features. With the vision, we run a visual odometry algorithm that recovers automatically the scale with the pipes, given the pipe diameter. We extract circle-like features that are the ones represent joints using difference in the color space, and then we describe them with circles. Once both modalities agree, they can verify. It's verified, and we can do more interesting things, such as mapping these construction features in a given reference frame. So, for more details, please visit my interaction session. Thank you.
Hello everyone, my name is Kimitoshi Yamazaki from Shinshu University, Japan. I will talk about grasping point selection from an item of crumpled clothing. My focusing task is to unfold an item of clothing by a dual-arm robot. The left movie shows one manipulation method that has been used. A robot picks up a corner of a clothing item placed on the table. Next, changing viewpoint by moving the cloth, and if it finds another grasping point, spread the cloth out. Oh, sorry. On the other hand, the right movie shows an unfolding motion that I aim to develop. If the robot can find two grasping points simultaneously, the spreading task will be more easier. To achieve this, I propose a grasping point selection method. In our assumption, an item of clothing is casually placed down on the table. A sensor to be used in this study is a 3D range image sensor, excitation sensor. The input data is just one range image, that is, color images and additional manipulation are not needed. The output data is grasping point candidates, which are represented by 3D coordinate systems. To obtain feasible grasping points, hem elements are used. From the range image, boundary parts on the clothing item is first detected, and hem elements shown as red line segments in the rightmost figure are detected. From these elements, grasping points are selected. This slide shows some experimental results by the proposed method. The method needs a set of training data. One training data consists of hem elements and manually given grasping points related to one range image. The upper images show input data, and the lower images show learning data selected as a similar shape. 5 colored points shown in the upper images show grasping point candidates. Right figures show results for another type of clothing. So please come to my booth if you're interested in my study. Thank you very much.
Hello, I'm Hideyuki Tanaka. My talk is about a new visual marker. Visual markers are useful tools in robotic systems. They provide ID and relative pose to a camera. The planar marker is easy to use, but planar markers have two big problems. One is instability, and the other is ambiguity. The orientation sometimes flips. The problem one occurs in frontal observation, while the problem two may happen in all directions. The cause of the problem is the estimation principle, which uses the marker shape. The shape does not always provide accurate and unique information about marker pose. So we solved both problems by introducing a new principle. We use variable moire pattern, which consists of a lenticular lens and a stripe pattern. As you see, the black part moves according to the seeing angle, so we can get pose information from BMPs. And we applied it to the visual marker. This is a novel marker, LentiMark. It consists of a conventional marker and 2 BMPs. The yellow bar shows the stable pose estimation by LentiMark. The LentiMark solved problem 1. But even LentiMark could not eliminate the pose ambiguity because the angle coverage of BMP is less than 30 degrees. In order to enlarge the angle coverage, we added 2 more BMPs to the new LentiMark. The phase and the cycle of BMPs are carefully designed, so it provides unique information and can eliminate pose ambiguities. I show the result of a comparative experiment. The AR Toolkit Plus is sole marker addressing the pose ambiguities. But as you see, the AR Toolkit Plus is very unstable, while LentiMark is very stable. In another case, the difference is very clear. The LentiMark is very stable. The AR Toolkit Plus does not work in the real situations, while LentiMark works well. And LentiMark is the world's first marker and that solved the biggest 2 problems. And it brings great benefits to many applications, AR, robotics, and measurement. You can see several demos and movies of applications at interactive sessions. Please come and enjoy them. Thank you.
Good afternoon, everybody. My name is Procopio Stein, and I'm going to present a work that I developed together with Anne Spallanzani, Vitor Santos, and Christian Logier. It is a study on leader classification and following. So what's the objective of my study is to improve robot navigation among humans. So what this means, like to enhance social interactions, to reduce computational costs, and also to overcome the limitation of some of navigation algorithms that are based on predictive approaches, like the freezing robot problem. This is a problem where, due to uncertainty, as you can see in red, in the fuzzy red dots, and due to narrow spaces, at some point the robot cannot find a path to escape the situation, although we know there is a solution for this situation. So the proposed solution is a bit different from the classical approaches. In this case, I will not try to plan myself. I will rather try to follow a human that's going to know how to deal with these situations. So try to select and follow persons to take advantage of their motion in complex and dynamic environments. The motivations of this proposal is that humans can easily navigate in such environments. We are able to deal with very complex social interactions. And the motion from people around and around us is very informative also about the environment. So here you can see a quick video about the robot is following someone. This is using a pedestrian simulation. So normally the robot would be blocked in the situation, but here it managed to smoothly navigate and become parts of the crowd as they negotiate the passage in this narrow corridor. So the question that I have to answer now is, how do I choose a leader to follow? So we know that people use very complex cues to see who we could follow or not. So my approach was to follow a bunch of people using a robot to register all this data, and then going to give this data to other humans to label them, these persons as good or bad leaders. I used an AdaBoost classifier to classify this set of data that I labeled. And using the output of this algorithm, I also study what are the criteria that we use to choose among leaders or to choose among leader candidates, so we can apply this information in robot navigation. So if you're interested in this presentation, I will be happy to answer some of your questions during the interactive session. Thank you.
My name is Woo Young-kwon from Hanyang University, Korea. My presentation is about human activity classification based on complex-based motion feature. Human activity recognition is a difficult problem due to several reasons. Sometimes signals often become very noisy. Moreover, same class of action might differ from person to person. In many cases, it is because of spatial and temporal misalignment. Well-known approaches such as hidden markup model and dynamic time warping simply use the data at discrete time series. Unfortunately, direct use of trajectory is very sensitive to noise and misalignment. Another approach is based on code word. Let me consider a human hand trajectory, shown as this. If we extract code words such as A, B, C, and D, the whole trajectory can be represented as the sequence of code words. It is more compact and allows for recognition than discrete time series. Then our focus is how to make code order. In general, a certain part of trajectory is more important than other parts. Finding the important part is the first step to make code order. Intuitively, an important part contains useful information describing the particular trajectory. One way to measure the amount of useful information is complexity. A path with high complexity is neither regular nor random. Both regular and random trajectory need very little information to describe them, so they cannot become important parts. When useful information is included in the data, the complexity will be high, and this can be regarded as the code word. Among many complex measures, we use predictive information. That is the time series complex measure. It is regarded as the channel capacity between the future and the past. So it is defined as mutual information between the future part and the past part. Parts with high complexity are learned as code word. This video is experimental result on open data set, MSR action pair 3 data set. We achieved 88.1% for average accuracy. It is higher than existing approach. For other data sets such as UCL data, GON data set and MSR action 3 data set, we achieved higher accuracy than existing approach. Remaining part of my paper is spatial temporal based classifier. More detail will be shown in the interactive session. Thank you for your attention.
Hello, today I'm talking about why layered hidden markup model can be enhanced by feedback mechanism. I'm Sang-Young Lee. This is our motivation. Here, good recognition framework can do the recognition of composite pattern and the training using a small training data set and the recognition from noisy or partial occluded input data. Finally, it can do the recognition in real time. Layered hidden markup model can be one of the good recognition framework because it can do the recognition of partial parts and they are composite. Second, the training of hidden markup models using small training data set. Finally, the recognition in real time if moving windows are offline. Especially Oliver said layered hidden markup model have superior performance than standard hidden markup models. However, layered hidden markup model may show the failed recognition due to partial mismatches of low-layer hidden markup model, like the problem of the blind man and the elephants. For example, let's suppose that these hidden markup model show partial mismatch because they don't know the fact that input data means the body part of the elephant. So recognition rate may be like this. However, at the next time, if this is also mismatched, then the recognition may be failed like this. So this problem can be resolved by feedback mechanism. For example, there are 3 partial mismatch like this. However, if we have these feedback mechanism, then these partial mismatch can make a correction like this. So our proposed method, if the higher performance, then standard layered hidden Markov model. To evaluate our proposed method, we used 24 classes of cooking activity like this. Here, our proposed method is a higher performance than standard layered hidden Markov model like this. The detail will be explained in the interactive session. Thank you.
All right, my name is Eric Martinson. I work for the Toyota Infotechnology Center in Mountain View, California. I want to talk today about guiding computational perception through a shared auditory space. Now, when I mean guiding computational perception, I mean pointing a set of sensors at a target in the environment and using object detection, recognition, and/or activity recognition to describe that object to a human user. But at the Infotechnology Center, we're particularly interested in blind people. It's interesting that we just had a talk about blind men, but I don't think it was intentional to be grouped together. When I say blind people, the blind people, though, can't tell you about visual space. They can't tell you about how things are located relative to each other. They talk about what they hear, so a new human-machine interface is necessary that allows a blind individual to make queries about things they hear in the environment. That is, by using what the person hears with what the robot can hear, we can build a wide baseline array for detecting sound sources from a combination of human and robot sensors. And as a result, what I will demonstrate for you is this results in better targeting for other computational perception systems than sound source localization alone. So what do I mean by combining data? Well, in this case, we have three different sources of data. We have data from a traditional sound source localization system, that is 4 microphones mounted on the robot. And we are also getting information from the human. We have pointing directions towards what they hear and spoken directions in front of, behind, to the left, which can also be used as evidence. By combining these things together, we can generate a singular position of interest to perception for further investigation. I won't go into the gory details here. I encourage you to come by my talk later on. But the results are that we saw improvements in both single sound source localization and when there were multiple sound sources. That is, when there was just a single active sound source in the environment, the introduction of the human data did not make it more difficult. It actually improved the results of sound source localization. It was better than sound source localization alone. Furthermore, when there were multiple active sound sources, only with the human input could the robot correctly pick a quieter sound source in the environment. That is, only by combining information from both the person and the robot could we correctly identify the source of interest to the person and point a camera or other sensors at the target. Thank you very much.
Hello everyone, my name is Yoko Sasaki from RSJ Japan. Today I will talk about the classification and identification of various robot sensing data. First, these are some examples of our mobile robot application. By using laser rangefinder, the robot extracts the surrounding objects for its motion planning. Also, humans are detected and the robot can observe its trajectories. The third one is auditory function. The microphone array localizes and separates surrounding sound sources from mixed audio signals. So from robot embedded sensors, we can gather segmented information of its environment. For example, 3D object as a point cloud, human trajectories, and separated audio sources with its arrival direction. The motivation of our study is environment recognition from these robot sensing data. To identify various sensor data occurring in real world, there are two main problems. First, all kind of event classes cannot be defined in advance. Second, each class has unique characteristics with varying complexity. To overcome these problems, we formulate non-parametric Bayesian model called nested infinite GMM. This is formulation of our model. It consists of infinitely many Gaussians in each GMM. It means flexible characteristics of each class. Then infinitely many GMMs. So number of classes and its complexity is automatically controlled from observation data. Let me show you some results. This is object identification of 3D point clouds. From 20-minute observation, trees or persons is identified. And also, there are part of ground, but these error segmentations are automatically classified. And this is a classification result of human trajectories. From 55 minutes observation, 22 classes are automatically detected. For example, passing L, looking around the exhibits, and the false detection of partition chains. Next example is audio event identification. From noisy recordings at Business Expo, microphone array extracts its sound, and it identified what sound is it at each frame from separated audio signals. Thank you.
Good afternoon. My name is Patrick Danès. I'm from LAS in Toulouse, in France. I will present you a joint work on the localization of multiple sources from a binaural head. So it's a fairly common problem in robot audition. We have here a robotics head with 2 microphones. We know there are Q sources in the environment, and we don't know their spectral contents. And we want to localize them, assuming that we have learned the noise beforehand. So here it will be azimuth localization. So the model is as follows. We have here the binaural signals. Here the contribution of the source on the left microphone, for instance. You can see the interaural impulse response, which accounts for the scattering you can see on the movie. And N1 and 2 term the noises. The transform of this interaural impulse response is, of course, the interaural transfer function, which depends on the source azimuth. So the data is the channel time frequency decomposition of the 2 binaural signals. We call it capital Z. We make some assumptions, the most important being that we don't assume that the signals are stationary, but we assume that they are stationary on very short time snippets, which is not very prohibitive. So last year we showed that if we have only a single source, the problem is tractable, so the azimuth comes as the maximum of this beautiful likelihood here, which depends on the data and all the spatial parameters that we want to determine. So this problem was easy because it was separable. That means that though we had to determine the spatial and spectral characteristics of the source, we could express the most likely spectral characteristics as function of the azimuth. In the multiples case, we have Q azimuths to determine. We have tons of spectral parameters to determine also on time frequency bins and for all the sources, and the problem is no longer separable. So we propose a solution based on the WDO assumption. The solution is an iterative solution with the expectation maximization algorithm with the latent variables accounting from which sources contribute to each time frequency bin. We have 2 very nice properties. And at the end, we get these kind of things. So if you are interested, I will be glad to explain you in more detail. Thank you.